anticipation. Yeah, I know, right? What are those guys called?
Okay,
Yeah.
we're live.
Okay. Hey, everybody. Welcome to the general meeting of the Los Angeles Astronomical Society of the date June 16th, 2025. Thank you all for coming, whether you be here at the Leonard Nimoy Event Horizon Theater or out in Zoom land. Look at it. Everyone's starting to show up. This is great. Awesome. I am been waiting all week for this meeting because there's a lot of really cool stuff, but you have to wait for it. But we have a great presenter also. It's going to be really cool. As is tradition, I need to call out and definitely not shame the new members. So who are the new members that would like to make themselves known? Any new members? First timers? All right, we got some. Okay, here we go. What is your name and what brought you to LAAS?
Hi, my name is Myra. What brought me is the universe has always just been a really personal interest of mine at a young age. So I'm glad that I can be a part of a group that shares that same interest. So thank you for having me.
We do share that interest. This is great. Who else? Awesome.
Hey, I'm Jesse. I joined back in 2020, but this is my first meeting, so sorry about that. I joined because I'm interested in telescope making, and I haven't made a telescope yet, so I bought one, and now I'm having fun using it. And yeah.
Awesome. You picked a great moment in the club to join for that reason because we're finally doing that again. So, yes.
Hi, I'm Aditya. Nice to meet you guys. I haven't actually officially joined yet. I'll do it very soon. I'm here as Mr. Phipps's guest today. I've been to all the star parties and stuff, and just really awesome stuff. I've always been interested in astronomy and stuff. So, yeah, I've just this is how I found this club, and yeah, I'm looking forward to all these meetings and stuff.
Amazing. Anyone else? Oh, we got one more. Can we just jump? Yeah. Thanks, man.
Well, I'll let my son Jack talk, but I'm Brian, and I'm here because my son's very interested in it, and Larry brought us. So here you go, Jack.
I've been interested in astronomy for a while, and then I met Larry, and we started coming with Larry. So that's how we got here.
Oh, we got it. Don't worry about it. We're good. Anyone else? Got one over there? All right. I'm making the trip. It's worth it. It's worth it. I'm only slightly above that.
My name's Jacob. I've been coming to Griffith for a while now, but I've been going to some events at Mount Wilson. I went to the SphereX talks and telescopes and met a volunteer up there, and she told me about the society, and I joined about a month ago, but my first meeting. Excited to be here.
Thank you so much. It's always so cool to see new members. And Larry, it's good to see you here. I usually see Larry up at Lockwood. It's really awesome to see Larry here. Okay, so as is tradition, I will list our agenda.
You got
And
Zoom
then we
meeting.
will get right.
You got
Huh?
new members on Zoom too.
Oh, I'm so sorry. Who do we got in Zoom land? My apologies. That is new and would like to introduce themselves. I think I recognize everybody though.
I'm new.
Oh, Sophia.
Hi. I'm Sophia. I'm new. Are we just doing general introductions?
Yep. Why, do you have something specific you want to say?
No. I was at a star party like a couple months ago. And I was a part of the Astronomy Society in Cincinnati for a while and using telescopes over there. So excited to get involved here. Do more of the same.
Well, that's awesome. We're happy to have you. If you have any questions on how to get involved, definitely reach out on the groups IO if you are on there. That's a great way to do it. Or show up at Garvey on Wednesdays, then we'll keep your calendar full. Don't worry.
Sounds good.
That is
Thank
what you
you.
desire. Hmm? Okay. I think everybody else is. Oh, wait, who's Aaron? I don't recognize Aaron. Are you new, Aaron?
Hi, I've been to a few other virtual ones. I've just been shy and haven't officially introduced myself. But I am just an enthusiastic stargazer. I've both in New York and San Francisco gone to different stargazing events and lecture series, and so I'm excited to be a part of this one.
Well, thank you for joining us. Excellent, excellent. I think everybody else looks to be a grizzled veteran of sorts. So with that, now I will list the agenda, which will consist of getting directly to our guest speaker, and then we will do some announcements, of which I am excited to announce. Then I will announce my 2 favorite members of the month, and then we will get to door prizes. Then I will tell you what the heck is going on in the coming month, and then you get to leave. So, with no further ado, I'd like to introduce our guest speaker. You can clap.
Okay. Let's see if I can do this here. Good. Yeah, thank you for having me here. My name is Andreas Faisst. Should I show it? Yeah. Okay. Get it out. I probably have to stand here, right? Okay. Okay, I try not to move, else I'm going to leave Zoom. Okay, so yeah, it's good to be here. I think I gave the last talk in 2018 here at Griffith. And there's a lot of new things I actually want to talk about. Some exciting new telescopes that have been launched. And so in the next, how much time do you have? Like an hour, 2, 3? Okay, in the next, so until midnight, I have time, right? I want to tell you something about the secrets of galaxies and whether we can solve their mysteries or not. And so first I want to start with a very simple question. Where are we? We are here at Griffith Observatory. That's a real picture. It's not AI. This is AI. Where are we in the universe, right? And so these are some big questions that we have as humans, right? So where do we come from? You know, why are we here? Are we alone? I'm probably not going to answer the last 2 questions, but maybe the first one. And one big strength of humanity is, you know, curiosity. But some people said, right, you know, the universe, how it formed, you know, how our Milky Way formed. We are curious. And so let's be curious and let's take a journey to explore the mystery of our universe. And let's start where we are, right? So this is our Milky Way. It's a nice spiral galaxy. It has about 400 billion stars. You're going to see here. Some of them you see on the night sky. And so we are here. We are about 28,000 light years from the black hole, but don't worry, it's fine. It's far enough away. So the whole Milky Way is about 90,000 light years across, right? And so just to give you an idea about the distance, relatively small distance. So if you stand on one side and you have a long distance relationship with somebody else on the other side of the galaxy, and you call that person, it takes about 90,000 years, right? And then it takes another 90,000 years until you're here, right? If they're home or not. But by then you probably changed your phone, right? And you can't even receive the call anymore. So too bad, but let's look around, right? So we are here at the red dot. We look around, what do we see? Well, first, if you see right in the center of the galaxy, we don't see much, right? There's a lot of dust around it. the black hole is here. We can't see it. Maybe better. But if we widen our view and we look on the night sky, there we go. There we go. We actually see our Milky Way. It's an edge-on of our Milky Way. Shouldn't move. Here, there you go. See it? No? Oh, no? Oh, there we go. Wrong monitor here. So that's the edge now from a Milky Way, right? You see all the dust, the dark areas. You see all the stars. You see the center of our Milky Way. It's right there. The black hole is right here. And you see a couple of different things, like the small and large Magellan clouds, which you see from the southern hemisphere. You see various star-forming regions that appear blue. I'll tell you later why they are blue. And if you zoom out even more, we see our local group, right? So we are here in the Milky Way, small Magellanic clouds, large Magellanic cloud, some other galaxies, Triangulum, and then this big one on the upper left side is the Andromeda Galaxy, right? It's our closest neighbor. I'm about 2.5 million light years away. So don't even start doing a long-distance relationship with somebody in Andromeda Galaxy. And so these are our closest and largest neighbors, right? So again, small, large Magellanic Cloud, Triangulum Galaxy, and Andromeda Galaxy. So that's what you see, right? Even here in LA, you can see the Andromeda Galaxy when it's a little bit clear by eye. It's actually a very nice target if you have binoculars or a small telescope. But let's stare more into the darkness, right? Let's look at this little square there and see what's there. And so that's an image from the Cosmos Web Survey that I'm involved in with JWST. I will tell you later exactly the details. But what do you see there? You see a lot of galaxies, right? So you actually see the stars from our own Milky Way. They're like here. It's hard to see here. I'm too old for that. There's one here, one here. Well, everything that has like spikes, right, from the optics. Let's zoom in a little bit more. Then a bit more. Then a bit more. So you see all these nice galaxies, right? So is it really darkness? No, it's actually not, right? There's a lot of things out there. A lot of galaxies. Spiral galaxy. You see a galaxy that looks a bit red. We call them old galaxies. They're red and dead. No more spiral galaxy. And then young galaxies here, and then very compact galaxies here, right? And so what we observe when we look into the darkness of the sky is a variety of galaxies. And we ask, how are they formed and how are they related to our Milky Way? And so in the next 50 minutes or so, I want to touch on a couple of topics. So first I will give you a big picture of galaxy formation evolution, what we know today. And then I will show you a couple of telescope basics with what we observe with the JWST, James Webb Space Telescope, and how do we measure the masses of galaxies, how much star they're forming, and so on. And then at the end, I want to show you a couple of very recent results that we found, and that's based on this Cosmos Web field that I was showing before. So first, how did the universe form? Well, it all began with a Big Bang, right? And so we think that this Big Bang happened about 13.7 billion years ago. And shortly after this Big Bang, the universe started to expand. It was heating up, and then it was cooling down. And about 100 million years or so after the Big Bang, the first stars were formed. And another maybe 100 million years later, you see the first galaxies form out of those stars. And then about 9 billion years later, after that, our own planet system formed. So here's a timeline, right, from 0 to 13.7 billion years. If you're interested, dinosaurs, they lived about 250 million years ago when they appeared. It's about the same time I just realized after the Big Bang, after when galaxies formed, just the other direction in time. And the important thing in the universe is this cosmic web of dark matter, right? So dark matter is a part of all the matter in our universe, so let's say the total energy, right? So about 70% of the whole energy budget of the universe is dark energy. Dark meaning we don't know what it is, that's why I call it dark, we can't see it. Then it's 26% dark matter. It's also dark because we can't see it and we don't know what it is. So we usually call everything dark that we don't know. And then we have ordinary matter, which is us, right? The stars, the gas, the dust, everything around us that we can see, right? And so the dark matter, so those 26% hold the universe together. It's really like a spider web that holds the matter together. And that's what we call this cosmic web structure. This structure depends on what we call cosmological parameters that we can measure or try to measure. And depending on those parameters, the interaction of dark matter changes. The cool thing is dark matter only interacts via gravity, right? So it doesn't have friction, nothing, it's just gravity. So what keeps us on Earth, this is what dark matter, does. So that's why dark matter is very easy to simulate in a computer, right? You don't need gas physics or stellar physics or any weird things, it's just gravity. So people have simulated dark matter a long time, and I'm showing you here one example that's from the Millennium simulation, which is also now 10, 15, almost 20 years old. You see on the bottom the time after the Big Bang. So this is 200 million years after Big Bang. You see the dark structure. These are what we call voids. So there's not much dark matter. And then the light structure that's a bit brighter. This is where there's more dense dark matter. So the brighter the image, the more dark matter there is, right? And you see this like structure appearing. So if we now go forward in time, so we're now at 1 billion years, you see how the structure changes, right? So as I said before, the dark matter is just gravitationally bound, so it just clumps together whenever there's an overdensity of dark matter. That's where the dark matter goes. And naturally over time it builds this web structure that you can see here. So now we are 4.7 billion years. And that's how it looks like today in the computer. So you see this like massive clumps of dark matter and these overdensities. And that's where galaxies form, right? So you have this dark matter and then you have the gas around it. And the gas basically gets attracted to those dense regions. And when you contract the gas and make it dense, that's where stars are forming, and then eventually galaxies. So this is, zooming in on this very dense dark matter region, and this is an actual picture, right, from the James Webb Space Telescope. It's an Abel cluster, 1698. Doesn't matter. It looks nice. But you see this, there are a lot of galaxies there. You don't see the dark matter because it's dark, right? But you see this, 10, 20, 25 galaxies clumped together at one space. And so they formed in one of those dark matter potentials. And so now the question is, okay, so we have now the structure of the universe. So how do galaxies actually form? And there are different ways a galaxy can form. You can have, it all goes to star formation, right? So you can have internal star formation, so you compress your gas, you form stars inside the galaxy, and that's how you grow the galaxy. It gets more massive, more stars. Right? When I say the mass of a galaxy, I basically count how many stars there are. For the Milky Way, it's 400 billion stars. You can also accrete galaxies, small galaxies, onto the bigger galaxy. Continuously. That's what we call, there's like an accretion rate of mass onto the galaxy along its lifetime. Or you can have a bit more rarer events, but more exciting. These are major mergers. So they are big galaxies that merge together and basically make one galaxy, right? So you basically increase your mass of the galaxy by a factor of 2 within 100 million years. So to simulate this, galaxy formation, it's a bit more complicated, right? Because now we have not only dark matter, which plays not that much a big role on the smaller scales of the galaxies, but you now have the gas, you have the stars, you have friction, you have all kind of stuff, right? And so it's computationally a bit more expensive to simulate those galaxies. But it has been done, and what I'm showing you here is a movie. Up is the redshift, which I explain you later what that is, but it's kind of running over about 13 billion years. It's much faster, actually. Don't worry, we are done soon. But you see here how the galaxy accretes the matter. So what you see is gas and stars. You see those little clumps falling into the galaxy. This is this continuous accretion. You see how sometimes the galaxy pulsates, like now. And this is whenever there's a starburst. So when a lot of stars are being formed, and through the pressure of the stellar light, it pushes the gas out, and that's why it pulsates like this, like now. So you have a lot of also supernova explosion going on, and they expel the gas. You also see this dark stuff, right? That's dust that blocks the light of the stars in the galaxy. So we are now about 3 billion years from today. So we still have about 3 billion years to go. And now we went from this very turbulent thing to a nicer disk structured galaxy, as you can see now. And if I remember, yes, there is a bigger major merger happening right now, right? You saw the larger galaxy flying by. It might come back at some point. Yeah, smaller one. So that's really cool, right? So that's in a simulation. And so what have we learned? We have learned that galaxies evolve from being turbulent in the very beginning to somewhat less turbulent, more ordered, to like this smooth spiral structure. And so if you think of our Milky Way, so this is how our Milky Way might have looked like about 5 billion years ago, 10 billion years ago. So galaxies evolve from turbulent to smooth. They experience collisions, they experience starbursts, and they grow over time. So this was the simulation. And so you probably think, so how does he know that that's true, right? Well, now we have to go to the telescope and see if we can find those kinds of galaxies. So let's go back to our favorite field here, Cosmos Web field. And let's just pick a couple of galaxies, right? Just random galaxies, but now you can see how they look differently, right? So you see this very little red dot here on the left-hand side. That might be a galaxy that's a bit younger, right, in the early universe, and then it evolves like this. And then in the end, in today's time, you see how there are spiral galaxies or very massive, what we call spheroidal galaxies. So this is the flow of time. And here's a timeline, right, from 0.2, so 200 million years, to 13.7 billion years. So what is astrophysics doing, right? So what we try to do, we try to see how galaxies evolve over time. So we are connecting the dots, right? So how do the galaxies evolve over time? How do they get enriched with dust and metals, which are we formed out of? How do they change their rates of star formation? How do they die eventually, right? Galaxies, they don't live forever. And how does this all connect to the Milky Way? And so this is what we try to understand. But I showed you those images, and so the question is, how do we know that the galaxy on the left-hand side is older than the one on the right-hand side, right? So how do we know that? How do you know the timeline? Well, the question is, how do you observe galaxy evolution, right? So you saw in the movie that all takes about 30 billion years, and we don't have time to wait that long and see how the galaxy evolves. So what are we doing? Well, we are using that the speed of light is finite, right? 300,000 kilometers per second, or 186,000 miles. That means that the farther we look away, the more we look into the past. And so I have a little quiz for you on the next slide. Let's see Who knows? So I've listed a couple of examples of distances from the moon to an Andromeda galaxy in light seconds or light years. Who knows how far the moon is away from us in light seconds? 30, 1.5, 3, 1.1. Yeah, it's about 1.5. I rounded down a little bit to make it nice. What about the sun? 8, right? So you know the saying, right? When the sun sets, it's actually already set 8 minutes ago. We don't care about it. It's just, just that you know. What about Jupiter? 40, 45? Oh, it's pretty good. Yeah, 32. Oh, I was wrong, actually. I didn't practice the talk. What about Saturn? Yeah, 70, 80, right? Now Vega? 26, 4. 25? Oh. Not bad. What about the North Star, Polaris? That's harder, huh? Yeah. I also don't know, actually. 320. Okay, Orion, a very nice object to look in the telescope. Yeah. Probably better than my. So now but notice we are now light years and not light seconds anymore. And the Andromeda galaxy, you should know. Yeah. So, right. So, with the sun, it's easy. It's 8 minutes in the past, right? Andromeda galaxy, if you look at it, it's 2.5 million years into the past, right? So we use this for galaxies too. But obviously we don't stop with Andromeda, right? We can go further. So what we are doing, we look at galaxies that are very far away, like those bunch of galaxies here, 13.3 billion light years away. Then we look at galaxies that are 10 billion light years away, and then we look at galaxies that are 4.5 billion light years away, about when our solar system formed, right? A bit earlier than that. And so we're connecting those, right? So they're not the same galaxies, obviously, but we assume that statistically they evolve from, snapshot to snapshot in time. And that's how we statistically can study how galaxies evolve over time. But now the question is, how do we measure the distance of a galaxy, right? And you probably know of that, right? So Edwin Hubble a while ago, and also others noticed that distance, so the farther a galaxy or an object is away from us, the faster it moves away from us, right? So you have this speed versus distance. It's a nice linear correlation in log space here. So if we know the speed, the radial speed where an object moves away from us, we know its distance, right? Easy. Not that easy, but for tonight it's like this. So, right, you have heard from Doppler shift probably in school or later. So, that's the example with the ambulance that drives by and you hear the sound in a different pitch, right? When it approaches you or drives away from you. It's the same with the light. If a rocket is coming towards you, it's blue. If it's not moving, it's just whatever color it is, white. And if it's moving away from you, it's red. I always make the joke when you're driving a car too fast towards the red light, it turns blue, but it doesn't matter. It's not turning green. So. Okay, so now we can substitute here those variables. So obviously this redshifting, right? It's called the redshift, and that's the redshift I was mentioning before. So the higher the redshift is, the more redshifted the object is, so the farther it's away from us. So, and that's now what we use, right? So we can measure the redshift of a galaxy by looking how redshifted its light is. And then we can read here off basically how far it's away from us. And because the speed of light is constant, we know how far back we are looking into the past. So today we are at redshift 0. The first galaxies formed about redshift 15 to 20. The currently highest redshift galaxy that we have found with the JWST is about redshift of 16. Okay, so now we can go back here, and we can say, when we now can say, now we see in 3D, right? So we can assign distances to those galaxies. So we see some of them are 3 billion years away. They look kind of big, right, as expected. But then this guy here is 7 billion light years away, right, but looks bigger. So that's funny. And then some of those smaller here, they are 12.5 billion light years away. That's about the redshift of 6, right? So this is how the galaxies look like at redshift 6. Obviously small because they're far away and very faint, but they're also very compact because they are physically small, right? So they grow over time. So yeah, and now you know how I made this slide here because I know the redshift of those galaxies. Namely, this is redshift 7. Those are redshift 4, and those are redshift 0.5. So basically today. And now we have this timeline. And we can use this now to study, right, how the galaxies evolve. Although they're not the same galaxies, but statistically we think that they evolve into each other. And so telescopes are time machines, right? So next time you look into a telescope here or at an event of the LAS, you're always looking into the past. That's pretty cool. And the radar, your telescope can catch the light, right? Depends on your sensors in the telescope. The farther you can look back because you see the redshifted light. And that's why Hubble, with the Hubble Space Telescope, we stopped about here. That's like a redshift of maybe 10 was the highest that we could see with Hubble. With JWST, we can look much farther where the first stars were formed, redshift 16, redshift 20, right? Because it's much, it has a higher sensitivity in the red than the Hubble telescope. Okay, so now the question is, okay, so we know where the galaxies are, how they line up in time. So how do we measure the galaxy properties, right? And what do we want to measure? Okay, so we want to measure and, you know, understand the evolution of different parameters. So first, the structure of the galaxies, so how they evolve from turbulent to disk, how many stars there are, how much dark matter there is in the galaxies or around the galaxies, how many stars they're forming, how much gas they have, how much dust they have, and also what's the metal content of galaxies, right, which is ultimately making everything that we are out of. And so looking at the structure, you already know this. That's another nice example here, how galaxies from redshift 10 to redshift 0 evolve in terms of structure. And an interesting thing that I'm going to tell you in the end, there is a very abrupt change in structure very recently. Actually, it starts already at redshift 2. So you see this spiral galaxy here. It could also look like this spheroidal galaxy, pretty boring. And that's when galaxies die, right? That's very sad. But they basically turn off their star formation. They don't form stars anymore. Okay, so now how do we measure those galaxies' properties? So galaxies look different at different wavelengths, and we can use that because each wavelengths are telling us something. So on the left-hand side, you see the visible light as we would see it with our own eyes. On the right-hand side, you see the same structure in the infrared light. And you see, you can look through the dust. And you see the stars inside this star-forming regions. And that's pretty cool. So another quiz for you. So that's a galaxy imaged in the infrared. So heat, or, well, it's not very hot. It's cold dust, actually. Does anybody know what galaxy this is? No? M41? Yeah? Somebody else? Yeah? M31 Andromeda. Okay, this takes a while. What? Yep. Right, so this is how we see Andromeda with our eyes through the telescope in your backyard. Well, not like this, obviously that's Hubble, but anyway, you see the central part. But in the infrared, it looks much different. And if you remember, all the dust is it's like rings, right, in those regions here where the stars are being formed. And so that's pretty cool. And so that not only works for infrared, we can look at any different wavelengths, and the galaxy looks different. So who knows what this galaxy is? Whirlpool? Yeah, I think so. Yes. Does it say? It says, yeah. Right. Cheating. Okay, so this is all the same galaxy, but you can see in the radio on the left, that's the cold gas. The cold gas sits in the spiral arms. That's where stars are formed. Because for star formation you need gas, cold gas. You first have to cool the gas so it can contract, get dense, and then you form the stars. The next is the infrared that I showed you before. So that's the cooler stars, right, and a bit of dust. And then you see the optical light. That's how we see the galaxy, right? And then if you go into the UV light, you see very hot stars, young stars that are formed, very massive stars. And if you go even farther into gamma rays, you see all the hot gas hovering around in the galaxy. That can be, for example, shock heated. So if two galaxies collide, you can shock heat the gas, it gets hot, and it emits in the gamma rays or X-rays. Okay, so now let's put everything together. And so what we observe is the so-called spectral energy distribution. It's a horrible word, let's just say SED. Okay, and that's the brightness of light as a function of increasing wavelengths. And that's here, that's actually a real, it's actually a real galaxy. But you have to believe me. So you see brightness versus wavelengths in micrometers. Brightness doesn't matter much, just up is more bright. And now you have these different regions, right? The optical light, where the stars are, then the infrared light, where the stars and dust are, and then the mid-infrared, and then the infrared light, which is where the dust emits. And I can give you the word of the day, polycyclic aromatic hydrocarbons, or PHs. These are dust grains. You don't have to remember that, but it's cool because they poke out in the mid-infrared. These are molecules that you can measure in galaxies. But what we see with our eyes is only this small part, right? That's what's visible to us. And so now let's see what happens if you have dust in your galaxy. So this is an SED of a galaxy that has little dust. And when you add dust, this happens. Right? You can flip here. It kind of tilts, right? Because dust is, so you absorb the light in the blue with dust, and you re-emit it in the red, so it comes out at the infrared light. And that's how why the SED tilts this way. So you get this infrared bump here when you have dust in the galaxy. And you have this red slope here, which means more flux in the red, more bright in the red wavelengths when you have dust. So the cool thing is when you have star formation, the same thing happens. Because star formation, when you form stars, they are young, they're hot, they are blue, and you heat the dust, so you have more dust emission, and you have a bluer slope here in the optical light. And so when you now look at the star-forming galaxy, it looks like this. When you look at the galaxy that doesn't form stars, it looks like this. Kind of boring. You also see those peaks, so those are emission lines. These are very specific wavelengths where, for example, the hydrogen atom emits light. Probably have heard of H alpha. I think that's the light right here, the line right here. So you need energy to excite the molecules and atoms at those specific wavelengths. If you don't have the energy, like in a galaxy that doesn't form stars, they're gone, right? It's just flat. Okay, so it's all put together. So you have blue star-forming galaxy and the red galaxy that's not forming stars. We call it passive galaxies or quiescent galaxies or quenched galaxies because the star formation is quenched. And so if you measure this spectral energy distribution, you can tell if a galaxy is forming stars, how much dust there is, how many stars are being formed, and so on. The age, right? That's basically like a DNA, almost. And to measure this SED, you need a lot of different telescopes, right? Because different wavelengths. So Hubble, JWST, you probably know Spitzer is in infrared, and then ALMA, you see here, is basically covering this far infrared peak here. So in order to understand galaxies as a whole, we have to take data from all those telescopes. Somebody said they were watching a talk about SphereX on Mount Wilson. It's also here. It's actually a telescope I'm working on. I'm going to have a data release actually next week. So those are actually telescopes that are being with significant contribution from Caltech in Pasadena and also obviously JPL. And some of them are even operated from Caltech in Pasadena. But all of them has a very big involvement with NASA, obviously. I should also mention Euclid, which is a new telescope that's already has a first data release, and that's scanning a lot of the sky. The cool thing what we can do with JWST is to look in the optical light and measure those emission lines. And those are really like a DNA fingerprint of the galaxy. So you see those emission lines here zoomed in. That's a galaxy at redshift 8.5. It looks like this, pretty boring. But you see the neon lines here, hydrogen, oxygen, and probably also some metal lines. So if you put this all together, you can measure how metal enriched those galaxies are, how evolved they are, and eventually how similar they are to our Milky Way. Another cool thing here, so that's a comparison of the Spitzer Space Telescope and JWST. Spitzer was actually operated from Caltech 2003 to 2020, and then it was turned off. And then JWST came online, right? And you see how different those images are, right? I think the left one is multiple hours with Spitzer, and the right one is, I think, 15 minutes or so with JWST. And you see the difference, right? So we can learn now a lot about the structures of the galaxies using JWST. While before with Spitzer, we knew the brightness, we knew how bright they are. You can do a lot of things. You can find high redshift galaxies, you can measure their masses and so on, but you cannot study the structure of the galaxies and the resolved properties. And I showed you this before. Because JWST is working in the infrared, it can look at much farther distances by looking at galaxies that are much more redshifted than what Hubble could do. So, okay, so I talked a lot about theory now. And let's look at some data. So this is a bit of advertisement for myself and my group, my collaborators. That's the Cosmos Web Field. We also have like buttons here. That's the largest ever field that has been surveyed with JWST. If you think it's not that large, it's about the size of 3 full moons, so like a thumb. But for JWST, that took 250 hours to observe this. It's about 10,000 images. Basically, when you do a mosaic with your panorama mode of the camera with the phone, it's the same thing, what we did. We found about 800,000 galaxies in this field. And basically from redshift 14 to almost today, right, redshift 0.5 or so. So, more than 13 billion years of cosmic time that we could probe. We saw single galaxies, but the cool thing about this is because it's such a large field, we can study this large-scale structure. So we can see how the galaxies group together, and from that we can reconstruct this dark matter cosmic web. That's pretty cool. We had a data release a week ago, and maybe you've seen me on KTLA. I gave a morning interview. It was 8:15, it was very early in the morning. I look a bit tired. Yeah. Yeah, you can watch the interview if you scan the Zoom, the QR code. But that's not that interesting. Let's actually look at this map. So what we also did is we created this interactive map. It's like Google Earth or whatever universe. That we can zoom in and dive into this image. So I'm trying to do this live here. It's probably going to fail. I hope you can see it on Zoom. See it on Zoom? probably. Okay, so it's really cool. It's like Google Maps. So you can go in here, right? You can zoom in. You can find your favorite galaxy, like this one. That's like a spheroidal galaxy. It's probably one that's pretty dead, right? Doesn't form much stars anymore. But then you see these guys here, you know, this spiral galaxy here. And you see those red dots here as well. Like, it's not a red dot, but like this one here. It's red because it has a lot of dust. So from looking at the SCD before, you see you remember when you have a lot of dust, you get more infrared and less UV and optical light. And that comes out in this RGB image. So I have to maybe say, so this is an RGB image from three different JWST filters. So we just put them together and make a nice image. I saw one before. Okay, here. So look at this one. Look at this thing. That's a galaxy that's probably redshift 8 or 9 maybe. So 12 billion light years away. It's right here. So yeah, you can feel free to go to this web page. I show it afterwards. And you can really zoom in here. You can use it for your presentation. You can take screenshots. There are a lot of cool things you can do that you don't have to know. You can add like, you see how all the galaxies that we extracted, you can get lost, you can click on it. This might fail now. You see this, what I showed you before, this SCD, right? That we see here, we measure this. We measure the redshift, but this is for experts, if you don't have to. You can just have fun and look through it. Okay, I'll try to go back here. There we go. Yeah, so that's a cool thing. So finally, so what did he find with JWST and also on this large field that I was showing you before, in this Cosmos Web field? So there are 3 interesting things, I think more, but 3 I want to highlight. So one of them is, you remember how our galaxy is this nice disk galaxy with this nice spiral structure? We found that those types of galaxies have existed much earlier than we thought before. Because, you know, in order to form this disk structure, it takes time, right? As you've seen from the simulation, right? It's very turbulent, and then at some point it forms this disk. We have seen them now much earlier than we have thought before, and that's mainly due to the resolution of the James Webb Space Telescope and also the red wavelengths. The other interesting thing is that, again, our Milky Way has this black hole in the center. Galaxies in the early universe had black holes that were much more massive than their mass, right? So you have the 400 billion stars, and you have your black hole in the middle. And so the mass of this black hole was much higher, much heavier than we have thought. And that's basically telling you that the black hole forms first. It's like chicken and egg, right? So black hole forms first, and then the galaxy forms around, right, and catches up at some point. So you have an overmassive black hole in the beginning. And then the other cool thing is that we found very massive galaxies. They're way too massive than what we thought. And let's do a little bit of math, but don't get scared. Let's go back to our dark matter structure. And so we can easily compute how massive the most massive galaxy can get. Okay, here it comes. So you have those dark matter halos, those overdensity of dark matter that draw in the gas, and then you form a galaxy in it. So this dark matter halo has 8 galaxies in it. Sometimes it just has 1. Okay, so don't be scared. So how do we calculate the mass of the most massive galaxy in a halo of dark matter? It's actually pretty simple. The only thing you have to know is, 1, how much dark matter you have. Oh, this is interesting. Oh. Okay, here. How much? Okay, no, I don't do that. It's too much exercise for me. So how much mass, how much dark matter do you have in this halo? Then what you also have to know is what is the baryon fraction? So how much stars and gas do you have as a function of that mass, right? So let's say, some percent of dark matter, you have the stars and gas. And then the other thing you have to know is that how efficient you form stars out of this gas. That's it. And that gives you the highest mass that you can expect of a galaxy. Some numbers, okay. So the star formation efficiency, this epsilon SF, you can measure it in the local universe. It's about 10%. Right. So this is, for example, you can look at Orion. How much gas do you have? How many stars did you form? Do the ratio? I mean, it's not that simple, but you get about 10%. And then the baryon fraction, that's pretty much set in the universe, right? You can look around, you can measure the dark matter masses of galaxies and how much baryons they have, so how much stars they have, how much gas. You get this ratio. The maximum dark matter halo mass you get from, well, those millennium simulations, for example. And as I said before, that's an easy thing to get because it's just gravity, right? So you can calculate this pretty easily. And from that you can compute the maximum mass. The problem is that some galaxies we found are like 8 times more massive than that mass. So that's kind of weird. So even if they would exist, they would be so rare, we wouldn't find them in this Cosmos Web survey field, right? So that's kind of weird. And there was also not enough time in the universe. They need more than 200 million years to form. If you are redshift 10, right? You only have like 200 million years or so to form the galaxy after the Big Bang. So either we can change our cosmology. So we have to change the expansion rate of the universe, the clustering, that's kind of complicated. We don't want to do that. And it's also, we have measurements that kind of confirm what we think about the universe. But one thing we can change how efficient galaxies are forming stars, this epsilon. Because that one was measured in the local universe. And now think of in the early universe, everything was much denser. And if you have a higher compression of gas, you can form stars more efficiently. And that's what galaxies do in the early universe. So that's probably the solution, but we haven't measured it yet. That's just a theory, right? So we had to refine our theory, basically, from how stars are being formed, or how efficient stars are being formed in the early universe. On the right-hand side, I'll show you 2 of the most massive galaxies at redshift 10. They're just red and compact. Okay, so finally, I want to show you a little bit what happens to galaxies. What's the fate of galaxies? So we go back to our nice diagram here. And so what happens here? Why they are so different? So galaxies will eventually die. It's like when you drive your car and you run out of fuel. That's it, right? There are no gas stations unless you have inflowing gas onto a galaxy, and they can maintain the star formation. But if you cut off the inflow of gas, then that's it, right? And so this diagram here shows you as a function of redshift, or time in the past, right? From the past to today on the left-hand side. And the number of stars formed per volume. It's like a log scale, that's why it's negative, but don't worry. So you see how stars form, the star formation increases up to redshift of 2, so 10 billion years in the past, and then it drops. And so about 10 billion years ago, that's when those first quiescent galaxies or dead galaxies appear. And so to give you an example, so a dead galaxy, how many stars does a dead galaxy form? 0, right? Our Milky Way forms about 1 to 2 stars per year, right? Still alive. Galaxies at redshift 2, they formed about 100 stars a year, or even more. So think of it like not the Orion Nebula, but Orion Nebula times 100. Like, it's gigantic, right? They're super efficient in forming stars, and they have a lot of gas. So one method how you can stop the formation of stars in galaxies is by colliding them. So through the collision, the gas compresses. So this is an example of the antenna galaxies. There are 2 galaxies that collided. You see the one galaxy here, the other one here. So in between, the gas gets compressed and forms more stars more efficiently, right? As I said before, compress the gas, you form stars more efficiently. It's like when you accelerate your car. You have fun, very fast, but you run out of gas faster. That happens, right, to the galaxies. So they have this starburst. They form stars at a much, much higher rate. Then they use up all their gas, and that's it, right? And if you don't have more gas streaming onto the galaxy, you cannot form stars anymore. And that's how they stop forming stars. So that's the summary, right? Two galaxies, smash them together, form this nice heart, and then you end up with these passive spheroids. So through this collision, you're basically destroying this nice disk and spiral structure. That's why those galaxies that are not forming stars anymore, they look like these boring, spherical things of star. And they're also red, as you can see here, right? Because remember from the SED, when you're not forming stars anymore, your SED turns red. Oh, here, right? So star forming, blue. Quiescent, you turn red. And that's why you move from a blue spiral galaxy to a red spheroidal galaxy. Okay, so, well, the question is then what happens to our Milky Way, right? So again, a Milky Way Andromeda galaxy, M33, is orbiting the whole system. Well, the problem is that Andromeda galaxy is flying towards us at about 200 miles per second. And now the last quiz question for this evening. How long does it take for the Andromeda and the Milky Way galaxy to collide? 3 p.m.? 4.5? Tomorrow? No. Maybe, never knows. Right. 4.5, yes. So still a bit of way to go, so no worries. So this is a simulation again from our Milky Way and Andromeda collision. You see the time in the future. So now we are at 1 billion years into the future. That's the Milky Way. Look at the color, huh? It's blue. Andromeda is there. M33, Triangulum Galaxy, sits there. So now we're at 2.5 billion years. Now it's becoming interesting. 3 billion years. 3.5. 4. Yeah, 4, and 4.5, roughly, right? They collided. And then obviously they come back, right? So they don't just stick together, right? Because it's mostly empty space. Right? The stars don't collide. That's funny. And they just go through each other. And then you end up with this red spheroidal galaxy. What I really like is look at the M33. It's still blue. It's like happy. It's like, another video. That's now the view from our Earth. It's obviously not real, right? But that looks like in 2 billion years, Andromeda Galaxy, Milky Way, right? Gets bigger. Doesn't fit in the field of view of your telescopes anymore. And then it becomes a bit messy. It's actually pretty nice, but we probably don't get there anymore. And that's the cool thing right here, right? 4 billion years. And then it's kind of boring. It's spheroidal. And also the two black holes in the Andromeda and in the Milky Way merged and make one bigger black hole, about, a factor of 2 more massive. And that's it. I hope it wasn't too depressing in the end, but it's also nice.
All right, so this is our traditional question and answer portion. Look at the hands going up. All right. Well, I'll make it easy for myself. There you go. Yeah.
2 questions. What were the emission lines in the spectra that you showed? Is it to do with the ISM? The neon lines. Okay. Are you aware of the recent papers that point to the fact that Milk Omida is not going to happen because it reviewed the rate of, I think, dark energy and added triangulum instead of the previous papers that I think looked at proper motions of stars? Thoughts?
Yeah, so the one I showed you, the simulation is kind of old, right? And there was this new paper that you were mentioning where they included M33 and I think another couple others. I think NGC, whatever that was there, and LMC and SMC, yeah. And so there might be I think it's like a 50% chance. It's kind of 50-50 if they merge or not, right? So they eventually, so what they did is they did a lot of simulations, you know, how they merge with like different initial conditions. And in about 50% or so, or 60, I think, or 40, or the other way around. As 40, they merge. They don't merge. That they don't merge. Okay, yeah. So only 40% they merge. I mean, they're still in the same big potential of gravity, so eventually they're going to merge probably, but not in 4.5 billion years. Yeah. Yeah. Yes.
The really big old red dots in what did they become?
So the ones in the early universe, that's a good question. The supermassive, yeah. So that's a very good question. So one thing I didn't show you is another way you can kill a galaxy by making it supermassive. And so the dark matter halo around the galaxy is usually about 100 times more than the stellar mass. So if you have a, oh, I have to do the math now. If you have a 1 billion solar mass galaxy, your dark matter halo is like 400 billion solar mass, 100 billion solar masses, right? And so what the dark matter halo does is when the gas comes inflow on the galaxy, it can shock heat it and it can heat it up. And you cannot form stars with hot gas. You have to cool the gas down first. And so if you are too massive, your dark matter halo is so massive that the gas doesn't cool anymore, so you stop forming stars. And so those galaxies in the early universe, they were already supermassive, so they're going to reach that limit very quickly, around redshift 5. So they just die, yeah.
Thank you for. Thank you for the presentation. I have a question about the Hubble constant, the Hubble parameter, in relation to the speed of light and what we see in the sky. Because the Hubble constant, is it constant? And does that change our view of the universe, of the speed of light and what we can see on like the cosmic, you know, the outer regions, I forget what they call that, cosmic, whatever. Yeah, background radiation. Are those old galaxies that, you know, like you said, just turned into gas, and that's what we're surrounded by? Just old galaxies are all just gas?
So you can't see me on Zoom, but you can hear me hopefully. Yeah, so this is a good question. So that's exactly one of the parameters that we can measure. But if you change it, then you're going to change this cosmic web and everything. So there is the Hubble constant, and there is also the, it's like a structure amplitude. So how much overdensities do you have with respect to the mean density? That's another parameter. And actually for the Hubble constant, it's interesting because we measure it at redshift of 0, but it might change earlier in the universe, right? And that's what we are trying to measure. So for example, the Euclid Space Telescope that has been launched a few months ago, was it already a few months? No, a year almost. That's trying to measure this evolution. Yeah. So we can pinpoint that, and then we can improve on our models.
Yeah, here's a question. When you're talking about the no star forming galaxies, those are all spheroidals, yeah? Okay, so if you measure no star formation, you could basically say that even if you can't really tell the structure visually, that, oh, that's a spheroidal. Okay, thank you.
He said yes.
Quickly, I get asked at star parties about the Whirlpool Galaxy when I'm showing that through the scope. Who is there anybody out there that really would know, or who is doing this that would know when that's going to collide? Just curious. Is there somebody in the I guess out there at the colleges or studying that?
I mean, yeah, we have. I don't know a specific reference or so, but there must be probably a simulation that can give that time scale. Yeah. So usually an interesting thing is what we try to measure is the merger rate of galaxies. So how many galaxy collisions you have as a function of time, and obviously we cannot wait and see what happens, right? So we do this simple n-body simulations to try to see how long it takes. If you see galaxies that are 100,000 light years apart, did they already merge? When are they going to merge? So this kind of simulations. But I don't know a reference, actually. We have a couple of people at Caltech who do this kind of simulations. So maybe it's worth looking there. Yeah.
I got him first.
When you were selecting the field for the Cosmos Web, was it random? Was it based on telescope availability at the time of year? My understanding is the Hubble Deep Field was they just kind of pointed it somewhere.
That's an excellent question. So it's not random. So there are two things. So one thing where we kind of screwed up a little bit, actually. You want to look how much dust is there in the Milky Way, and you don't want to take a field that's where you have a lot of dust in the Milky Way in the foreground, right? And so we kind of missed that spot a little bit. So one half of the field is a bit more dusty than the other half. Well, good. The second criteria was so the Cosmos Web field, it has been observed by many, many different telescopes. And so when, I'm not saying we because I wasn't alive then, it was 2003. I mean, academically alive. When they chose it in 2003, they chose a field that was equatorial, that you could observe with telescopes on the southern hemisphere and on the northern hemisphere. For example, this ALMA radio telescope, it's in Chile, right? And Keck in Hawaii is still on the northern hemisphere. So we choose a field that is kind of visible by all the telescopes on our planet. So those were the two criteria. No. It's much more equatorial. Yeah, it's at like 2 degrees array. Declination. Yeah. It's actually in sextans, the constellation.
Andreas, thank you for your presentation. So I always have this question, and I hope you have the answer, but with your work, can we see where our galaxy came from? Like I think you were alluding to this evolution of a galaxy, but I'm wondering, can we actually witness through the light where Andromeda or where the Milky Way came from? And part of another question is, have you seen the European Space Agency's simulation of how Sagittarius, a star, was created with the colliding of the two galaxies, Andromeda being the other galaxy. And what are your thoughts on that? Thank you.
Yeah. So for the first question, yeah. So what we usually do is we can trace back the evolution. So we know how massive our Milky Way is, what kind of the properties are, so how many metals there are, how much stars it's forming, how much dust, and then we kind of go backwards in time and find galaxies that are similar. And that way we can kind of trace back when the Milky Way was formed, for example, or how its mass changed over time, approximately how many collisions it had in the past, right? So we can approximately say this, yeah, with these measurements. The second question, I'm not 100% aware, or I don't know much details of that, yes. But that's galaxy collisions are very important now because also you have heard of the gravitational waves, right? So these are stellar black holes that are colliding. But eventually we also want to see how cold galaxies collide and how their supermassive black holes collide, right? So that's another data point that can tell us, how frequent those collisions were in the past. Yeah.
Let's see. I can't see the chat, but I'm assuming there's some Zoom questions out there. Spencer, can you, or can anyone that has a question go ahead and speak up on Zoom?
Actually, there's one from Teresa. What instrumentation would be the next step to move forward with this study?
How to move forward? So I think we found a lot of strange things, right? Like those very massive galaxies, and what we are doing now is basically to follow up on those with different telescopes. So Cosmos Web is pretty shallow in terms of sensitivity, right? And it's just imaging, so we haven't done spectroscopy. So look at actually at those emission lines. For example, for those very massive galaxies, what we're doing now, we are taking spectra with JWST to understand them better. So that's one avenue we're going. Look at the chat.
Spencer, what else do we got for
That's the only one. That was the only question in the chat. But people on the Zoom, feel free to unmute and ask your questions.
If not, then our timing is perfect. This is usually when we go to announcements. So, anyone else? All right, we got one more from Tim.
In your Cosmos Web catalog of 800,000 galaxies, since you just mentioned not doing spectroscopy, do you have like photometric redshifts and not spectroscopic redshifts? Are you starting to do spectroscopy now to fill out the catalog? If I go to the catalog and look, I'm not going to get a spectrum, I assume.
Yeah, that's correct. So those 800,000 are basically all from photometric redshifts, right? So we know the distances approximately, plus minus a few 100 million light years. But they are, because what I said before, the cosmos field has been observed by many, many different telescopes. There is spectroscopy, like randomly, and if you match that with those 800,000, we get about, a few percent spectra. Yeah. Not for the faintest things that JWST found, right, obviously. So that's the follow-up part.
Thank you. That's not the same, the first deep field image that was released, right? Is that the same, and it's just a piece of it that we see on the internet, the deep field with like the light around the brightest part, bending?
Yeah, no, that's not the same. Yeah, so what you're saying, this SMAX cluster that was first released, that's much, much deeper than what we see on Cosmos Web. It's about probably 10 times deeper, 10 times more time. But it's only one pointing of JWST, so it's tiny, right? Yeah. Yeah. So we call this like the wedding cake strategy, right? You start big and then you go deep. But if you go shallow, you can go wide. If you go deep, you have to go narrow.
Hey, it's relatable. Who hasn't gone deep into a wedding cake? Excellent. Thanks, Justin. He's loving it. He's loving it. Got the thumbs up. This is great. Okay, I think it's time to get on to announcements. So let's hear it for Andres. That was a really good one. That was a really good one. Yeah. No. Well, yeah. That was a guy knows a good analogy. Wow. Communicator. All right. That map, that was really amazing. And plus, I couldn't get away from the notion of a galaxy hosting its black hole. Kind of like that acai bowl I had for dinner hosting me before I annihilated it. All right. Well, it's not as good as the wedding cake, but whatever it is. Okay. Anyway, moving on. So we have a lot of big things going on with the club. I would recommend heavily coming to a family night this Saturday at Lockwood. We had last dark sky night electricaled out because we were having the electrical grid completely redone there, and it is done. We now have a fully stable electrical grid. We are safe from the fuzz. They can't come after us about that. Pretty awesome. All the pads have brand new GFIs there. If you run an astrophotography rig, you could leave your batteries at home. It's stable. It's good. All of the buildings have proper electrical outlets on the inside. So the C14 shed no longer has the cable running through the middle. The 26 shed now has electrical in it, and that's where we're going to host the potluck. So it'll be a vibe in there, that's for sure. And then the whole property has been weeded and graded, I think, yesterday. All our big telescopes are operational. Come and look through something huge. We have the big 26 that used to live here up there at a darker sky, so it looks even cooler than it did when it was here. But more notably, Spencer and Ted Moss, two of our board members, have rented the same style of bathroom that we have at Mount Wilson when we're there. So, yes, relieve yourself comfortably at Lockwood. A sentence I would never have imagined uttering, even now. Yet here we are. All right, that's amazing. One of the other big things I'm really stoked to announce is that the Los Angeles Astronomical Society now has a partnership with ZWO. Yes, this is awesome. They reached out to us because of all the efforts that all of us have been doing. I think we owe a debt to Dave Yackerson as our outreach coordinator for putting us out there. The reach that we have through Griffith Park with Mount Wilson, Santa Monica, the schools, Silver Lake, all of the things, they made us attractive to them. And there will be potentially our guest speaker coming up to give us tutorials on how to do astrophotography with their rigs. We will be receiving a C-Star S30, which will be going into our loaner program. So if you're interested in buying something like that, you can try it first. We'll teach you how to use it. And when the time comes that you decide to buy it, if that occurs, you will receive a 5% discount on it because of the club. That's really great. We will be beta testing for them on future products, and we will be getting swag from them. It's really exciting. They are all about us because we innovate when we do outreach, and not many other clubs do. That's for all of you. Rob, Alan, that's you guys making that happen. So we're reaping what we've sown, and it is a good reap. Okay, at this point, I would also like to invite any members that have party planning in their bones to join Laura May in planning our centennial next year. She's got them. It's in her bones. She wants it. She wants your help. We're trying to do something big for next year. We're almost 100 years old. We're so close. Shh. This is being recorded. 101 is cool too. But yeah, if you have any ideas or if you have any, well, let's start with ideas. Let's start small, then end big. Reach out on the groups IO or reach out to me. at president@laas.org. Now I'd like to introduce our bulletin dude, Mike J. Shalom.
It's editor. Hi. Just wanted to go and throw it out to everyone, including the Zoom people, that this month's bulletin is a little light. Everything that goes into that bulletin is contributions from you all. So you want something in there? Drop a line to bulletin@laas.org. That's me. And write an article. Send some pictures. Love to see it. Technically, it was yesterday. It was today's... tomorrow. But if you have something, just let me know, and I can get it in before the 25th when we publish. So anytime between the 17th, drop a line to the 25th. That's it. Thank you.
Awesome. And this can really be anything. I mean, there's a lot to being in this club other than being like awesome with the universe distantly. You can be awesome with the universe locally, or talk about a great experience you've had doing something, and like share something that you wish someone else knew about being in the club or with astronomy at large, or some cool thing with your gear, how you impressed your flat earther cousin or something like that. Any of these things are applicable because we're interested. I mean, all of us are here because we have a shared passion for astronomy or curiosity or what have you. And the bulletin is a really great way to reach the most amount of people. And I don't know, it's really appreciated when the bulletin is, call it plump with activity. Yes, explain how much you've enjoyed this meeting as I stare you down with a steely gaze from my pulpit of power. You enjoyed it, didn't you? That's a little surprise. But yeah, we do. We have a new place for your behinds up there too. We got new picnic tables. The what? The power grid is a big surprise? Yeah, you're right. That's a big surprise. But yes, there are new picnic tables up there, so you can eat, and you don't have to stand and eat over a trash can. Like that's not necessarily the vibe anymore. Larry's like, I got no problem with that. I've been doing that for 50 years. No longer, Larry. We have a proper place for you to sit and eat somebody else's food that they brought for you. Finally. That's right. It's a long time coming. It's the least we could do for you, bud. Okay. This is where I would like to, I'll bring on my good heavens portion of things, where I look into the eyes of the club membership and respond with a wink for the good deeds that they have done. And this month, I'd like to point out our members, Terry Colkin and Tony Cook. They are the two that are heading up the telescope building program at Garvey. And this is kind of a big deal, especially with our centennial coming up, that we're still building telescopes with like a little pause for like 40 years or whatever. But still, we're doing it. We're doing it. And actually, not only are they doing it and they're committed, which I was not so sure that was going to play out that way, but there's a lot of chemistry with that group. If you see them, they all know each other and they're just supportive, and they're learning. And they're these two guys, Terry and Tony, they're teaching it in such a way that the people in this program are going to be able to teach it going forward. So it's more than just teaching them how to build a telescope. They're teaching them how to teach to build a telescope, kind of like, like a Ben Kenobi, Luke Skywalker vibe with light, right? That's cool. That's a whole thing. So that's really awesome. I mean, when we were cleaning up Garvey, I put that poll out there to see if anyone cared about building telescopes again, and I was kind of using it as an excuse to get rid of all the telescope building stuff because I didn't think anyone cared. But I'm so glad that I was wrong. It's really, really cool to see, and because of Terry and Tony, we can move forward, and that is great. It's slow. It's slow going, man. I mean, we've got we've got a 10-year-old girl grinding a mirror right now. It's going to take time. It's going to take time. It's going to be great. I would suspect that we'd be done probably around year's end. And the club is fully supportive of them, and we can't wait to see that first class of telescopes come out. So, Terry and Tony, bless. That's really amazing. I think that gets us to door prizes, I believe. So, where's our maven of the tickets? Yeah. Door prize. Door prize editor.
Spencer, did you drop the link for the online?
Yeah, the link
awesome.
is there. So those of you in Zoomland, go ahead and register for the door prize. I think I only have about 14 registered so far, so there are quite a few more out there. So go ahead and register before
Okay.
I close it out.
We'll do the in-persons first. Okay, this first prize, I did not think it was going to arrive in time. Had pulled a lot of strings. It is a green laser. There's plenty more to go. Okay, the first number is 8335208. Do you just not want the laser? Okay, we can draw another one. Somebody's going to get a damn laser. Okay, number is 8335225. Hey, now he'll join the club for sure. There you go. Okay, next in-person prize is an online purchase from the gift store, $50 or less. Okay, the number is 8335240. No kidding. All right. Gonna do something unprecedented here. We're gonna do another online door prize, $50 or less.
We have to check to see if this is in the bylaws.
Okay.
It's in the bylaws.
Oh.
Executive order.
Wow. I thought I was going to get carted to astronomy jail. Some executive power right there. All right.
But I'm giving. I'm Robin Hood of the club.
All right. The winning number is 8335257. All right. I'll get your email address at the door on the way out. Spencer, whenever you are ready.
All right, so the first winner is Sophia Moak.
Oh, awesome. Two new members got a prize. This is amazing.
Okay, let's see.
Right? Yeah, that's the caveat. Reach out to bulletin dude at LAS.
So,
.jk.
Okay, what's the prize?
It's happening.
All the online ones are online. I'm sorry, the website gift store, $50 or less.
So how many are we doing?
3.
Okay. All right, let's see. Okay, next one is Terry Koken.
Hey, all right. There he is.
Yeah.
All right, and the third one is
Terry
Eric.
has plenty of grit just in his mustache. Enough to
Third
go
one is
around.
Eric Shalov. Eric, are you online?
I am. Thank you.
Okay, all right.
All right, Mazel Tov. Is it? Are we
Okay,
only doing
that's
three?
it.
Okay,
Three.
awesome. Good game, everybody. Now here's where I'm going to tell everybody what's coming up. All right, Sophia, you ready? I'm going to give you all the stuff. I'm going to tell you everything that's going on. I'm going to fill your calendar. The next general meeting is going to be here on the 14th of July. The next Griffith Star Party is going to be on the 5th of July. The next outreaches we have coming up that I'm aware of is going to be at Silver Lake on the 19th, 6/19. Our next big one where we're going to have music. We're going to have the Tiny Theater. Some guy's coming out with a little 8mm theater and a trailer, and he's going to be playing music to it live. It's going to be so cool. I've been waiting for it. It's called Davy B. Gravy's little little tiny cinema, and he's playing vintage spacey films. So it's going to be super great. We're going to have a jazz trio out playing. It's going to be a really good time. We have the Santa Monica outreach on the Santa Monica Boardwalk on this month on the 21st, which is also family night. So if you decide to keep it local, you can do Santa Monica. If you want to take part in all the big telescopes, come up to Lockwood on family night. The following week on 6/28, that's going to be Dark Sky Night, which is basically the same thing as family night minus the food and with a little bit more structure for dilated pupils. But also on 6/28 is the Mount Wilson Star Party. So if you want to keep it semi-local, you can go to Mount Wilson and do that. But that's also a 60-inch night, so if you only want to care about one big telescope instead of a bunch of small ones at that place, then you can participate with that. Reach out to Mount Wilson coordinator at laas.org and book that. If you want to participate in our zany board meetings where we have the most fun of anyone in the club, we have some fun. We actually called it out. Daryl said we were having fun. That was pretty crazy. And write an article about it. That's right. That's right. Write an article about the board meeting. I'll tell you what, that's riveting. And that's going to be on the 9th of July. And preceding that, honestly, I would actually, if I were you, attend the Lockwood meeting if you care about our dark sky site and want to participate in its future and the decisions made there. Joining the Lockwood committee requires absolutely no previous experience. I know because I did it. And I had no business doing it, but I did. And I learned a lot. And that's all. Everybody go home and look at that meeting. Look at that map that you made. That's so cool. That should fulfill the rest of your night. Good night. Oh, we got one more thing. We got a plug.
Just one thing. So this Thursday in this same place, we will have All Space Considered, the show that we run at Griffith Observatory. We will be discussing a couple things. It's on Juneteenth, so we'll be honoring Black astronomers. We'll be talking about a really cool Jupiter paper that came out recently. And our new curator, David Seidel, who's up there, will be discussing. Yeah, give him some claps. He will be. He will be taking the heat by discussing the current debacle of the NASA budgets coming up. So, watch it online or come here, leave some comments, call your representatives. Am I allowed to say this on our meeting? You already did it. Sorry. But anyway, important issues to discuss, so please attend or watch on the Griffith Observatory YouTube. Thank you. Yes, thank you for the reminder. One of our very own, Tim Russ, will be our guest. So he'll be discussing many things, astrophotography, etc. So please join us. We're going to have some really cool, exciting stuff. So yeah, good night.
Like she said, good night.
Everybody's leaving.
Hang on a second, Dave.
What happened to this?
Hang on a second. Hang on a second, Dave. Let me kill the live stream before you go on.